Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we are looking at Chapter 4, and we are doing entropy calculations, this time of an ideal gas. So to calculate the entropy change of an ideal gas, let's look at three different relationships that we know so far for an ideal gas. First, we know that the change in internal energy is C sub V dt. We know that change in enthalpy is C sub P dt. And finally, we know the ideal gas law, PV equals RT. And this may be rearranged in a couple of ways. Either V over T is R over P, or P over T equals R over V. Now, we want to substitute these into the expression for ds equals du over T plus P over T dV. So, du is CV dt, and P over T is R over V. Therefore, we can say that delta S is the integral of CV dt over T, plus R is always a constant, so the integral of dV over V is R times the natural log of V2 over V1. If we have constant specific heats, so generally this is for cases where the temperature change is not too significant, then delta S may be approximated as C sub V natural log of T2 over T1 plus R times the natural log of V2 over V1. Now I would like you to, on your own, repeat this using dH over T version of ds. Okay, so start here with the one that has dH over T and repeat that. And what you will find is that for constant C sub V, or C sub P, we end up with delta S is equal to approximately C sub P natural log of T2 over T1 minus R ln of P2 over P1. But I want you to do that work. Okay, if you run into any problems, let me know. Next, let's work an example. So if we have half a kilogram of air, treating it as an ideal gas, at 100 kilopascals and 300 Kelvin, under these conditions, it's actually going to be very close to being an ideal gas. And it's being heated at constant volume to a final temperature of 500 Kelvin. Using C sub P naught, so C sub P naught is the value of C sub P for air as an ideal gas. The naught indicates ideal gas assumption is 1.005 kilojoules per kilogram Kelvin, and R on a mass basis for air is 0.287 kilojoules per kilogram Kelvin. Use this to find the final pressure and the total change in entropy. Let's begin by using the ideal gas law. We know that P1 V1 over T1 is equal to P2 V2 over T2. And when we say that volume is constant, those are going to cancel out. So P2 will equal P1 times T2 over T1. Therefore, P2 is going to equal 167 kilopascals when you plug those numbers in. Remember, you must work with temperature in Kelvin. All right, so there's our final pressure. All I needed for that was the ideal gas law. The total change in entropy, well, we've been given constant values of C sub V, so delta S is C sub V natural log of T2 over T1 plus R natural log of V2 over V1. Using this, V2 and V1 are going to give me a natural log of 1, which is equal to 0. And so therefore, this is equal to C sub V natural log of T2 over T1. Now, the issue here is that I don't have C sub V, I have C sub P. But recall from our previous chapter that C sub V is C sub P minus R. Therefore, delta S is 0.718 kilojoules per kilogram Kelvin times the natural log of T2 over T1, both of those in Kelvin, and I get 0.3668 kilojoules per kilogram Kelvin. We want the total change, so we're going to take mass times the specific change. And so 0.5 kilograms times 0.3668 kilojoules per kilogram Kelvin, we end up with 0.1834 kilojoules per degree Kelvin change. Let's look at another example. For air at 6 bar and 1100 Kelvin, it's going to expand reversibly and adiabatically to 1 bar. And we want to know the final temperature if one assumes constant specific heats. And then we'll look briefly at what you would do if C sub P were not constant. So in this case, reversibly and adiabatically, this is that magic triplet, okay? When you have two, the other is inferred. You could prove that by going back to your definitions of entropy from the back at the beginning of this chapter. But these tell me it's isentropic, so delta S is equal to 0. Therefore, I can say that delta S is 0, but it's C sub P, natural log of T2 over T1, minus R, natural log of P2 over P1. Now, I've chosen to use this one because pressures were given. I could have obviously used the one with volumes, but I'd have to do a little additional work. In this case, I actually can do some algebra here that will be instructive again for future calculations that we may do. And so the natural log of T2 over T1 is equal to R over C sub P times the natural log of P2 over P1. And using laws of logs, I can bring that up as a power, right? This comes up as a power. And now I can take the exponential of both sides. I end up with T2 over T1 is equal to P2 over P1 to the R over C sub P power, or T2 is T1 times P2 over P1 to the R over C sub P power. In this case, that's 1100 Kelvin. P2 was 1, P1 was 6. Both of those were bar. R is 0.287. C sub P is 1.005. And this comes out to 659.4 Kelvin. So the final temperature is 660 Kelvin. Now, what would I do if C sub P were not constant? What I would need to do is go back to the definition. So T1 is 1100, T2 is unknown. I would need an expression for C sub P as a function of T, and that would equal R ln of P2 over P1. This being constant still, but C sub P as a function of temperature would need to be integrated. That concludes this video lesson. In our next lesson, we're going to continue looking at what happens with ideal gases that are reversible and adiabatic processes. Thank you very much for your time.